So continuing with our link layer discussion, let's talk about the Ethernet frame structure. So basically you have the following components. You have a preamble, the destination source address, you have a type field, which we're going to talk about. We have the payload, which is basically the IP datagram, and then some error checking, that's basically CRC, cyclic redundancy check code. So start off with the first field, and that's the preamble. So the preamble is going to have a very specific bit patterns. It's going to have 7 bytes, um, each with the pattern of 10101010, followed by 1 byte with a pattern of 10101011. So basically, the purpose of the preamble is to use synchronize Ethernet frames. So it's always assumed when you see this that we're starting an Ethernet frame, and this allows us to synchronize receiver and sender clock rates. So we'll talk about this a little bit more in later lectures. After the preamble, we basically have our source and destination MAC addresses. So basically, as far as receiving Ethernet frames, and we already talked about this already, but if an adapter receives a frame with a matching destination address or the broadcast address, it passes the data in the frame to the higher level network layer protocol. Otherwise, the adapter just discards the frame. The type field refers to the higher level protocol. We'll see this in our Wireshark labs, usually indicating IP, but if we're on another type of network, such as Novell or AppleTalk, we'll see a different value in the type value. And basically, there's CRC, the cyclic redundancy check, which is done at the receiver. If an error is detected, the frame is basically dropped. So Ethernet itself is unreliable and connectionless. There's no handshaking between the sending and receiving NIC cards. The receiving NIC doesn't send any acknowledgments or negative acknowledgments back to the sender. So the only way a drop frame is going to get recovered if the initial sender uses a higher layer reliable data transport, such as TCP. Otherwise, the drop data is going to get lost. So basically, reliability is not really taken care of at the Ethernet layer. And basically, Ethernet uses unslotted CSMA CD with the binary backup. And unslotted means that we're not trying to get some like time slot that we're trying to not collide over, kind of similar to what we did on the cable type connection. So you're going to probably be wondering, why do we even have CSMA CD? And we're going to get to that later, since we're basically going to be using Ethernet switches. So the Ethernet 802.3 standard has a lot of variations. So all of the different Ethernet standards have a common MAC and frame format, but they basically specify different speeds and different physical layers. So at the link layer, the Ethernet standards will use the same MAC protocol and frame protocol, but they will be different speeds at the physical layer. So these blue ones are the speeds for copper, and these red ones are the speed for fiber. And we're not going to get into the details on this right now. We will talk about these details in a later lecture. Okay, next two things we want to cover in our review is how do Ethernet switches work and how do virtual LANs or VLANs, how are they set up? So basically the Ethernet switch is probably one of the best things that ever happened to Ethernet, and probably one of the best things that ever happened to Ethernet network administrators. Basically, it took away a lot of the physical layer of troubleshooting um, and basically takes the whole Ethernet network and puts it into one box. So basically, the Ethernet switch is a link layer device. It basically works exclusively with Ethernet frames. It stores and forwards Ethernet frames. So it takes them in and forwards them to another port. It does this by examining the incoming frame's MAC address and selectively forwarding that frame to one or more outgoing links. When the frame is to be forwarded on a segment and it uses CSMA CD to access a segment, obviously if it and a host are the only two items on the segment, there'll never be a collision. But CSMA CD is used because you could possibly have an Ethernet hub on the segment, and it's also used to differentiate when to so you don't try to send and receive at the same time. So it controls that, but there's no chance of collisions because you only have two data sources, the switch itself and the end station is connected to. Unlike routers, where you have to tell a host needs to know where its default gateway is, switches are transparent to the end station, so they don't need to know about switches. Basically, switches act like basically the physical wire, and they're plug and play and self-learning. So unlike routers that require a lot of configuration, switches do not need to be configured. So they basically make the network administrator's job very easily. So switches are set up from a performance point of view. They have a backplane that allows them to support multiple simultaneous transmissions. So the hosts have dedicated, so each host has a dedicated direct connection to a particular switch, so there's no collisions on that link. The switches buffer packets, so it basically helps out with flow control. And the Ethernet protocol is used on each incoming link. Like I said, but there's no collisions because there's no contention for that link, and it's full duplex, so each link is in its own collision domain, so there's no concept of collisions within the switch itself. So it can basically switch from A to A prime and B to B prime simultaneously without collisions. So that means between the buffer size and the backplane size and the backplane speed, the switch can allow multiple simultaneous connections. And since there's no contention for actual physical media, there are no collisions that occur. So some important things to talk about relative to the switch's forwarding table is how does the switch know that host A prime is reachable via interface 4 and host B prime is reachable via interface V5. Well, basically, just like a routing table in a router, a switch maintains a switch table. and it's basically going to have the MAC address of the host, um, the interface to reach the host, and a timestamp. So basically you want to update this information, so we're going to have a timestamp and let these items expire and force us to get new information. So the important thing we want to talk about next is how are entries created and maintained in the switch table, and we're going to talk about that in the following slide. So basically the way it works is a switch learns which hosts can be reached through each of its interfaces. So when a frame is received, the switch learns the location of the sender, which is basically the incoming LAN segment. So as soon as it receives some data, it basically updates its switch table. So it basically does that by recording the sender and location pair in the switch table. So in this example, we have host A comes in on port interface 1. So when that port A fires up and first sends something over interface 1, the switch automatically puts that information in its switch table. So basically, when a frame is received at the switch, like I said, it records the incoming link and MAC address of the sending host. Then it uses it indexes the switch table using the MAC address. So it tries to find the MAC destination address. It tries to find the entry in its switch table. If for some reason it doesn't have it in there, first of all, if it does find it, it has to do two things. First of all, if it happens that the destination on the segment is the same as the source, it drops the frame. Else it forwards the frame to the interface that already exists. If for some reason there is no entry in the switch table, it's going to flood all of its ports, except of course for the one that it received the interface on, with the idea that eventually that host will reconnect. We'll send that message back to the. Well, first it'll get to the final destination, but what will happen is eventually that host will most likely talk to the original sender, and then that information will get updated in the switch table as well. So that flooding for that particular host should only happen basically the first time around, unless of course the entry expires. So here we have an example of host A wanting to communicate with host A prime. So when the frame comes in, the destination is unknown. If destination is unknown, it's going to flood, so it's going to go out all the other ports, so port 2, 6, 5, 4, and 3. If the destination is known, it's just going to send the message, just one link, in this case, link 4. So in the first example, this particular entry doesn't exist, and the second, so basically you have to flood all the other ports. And in the second example, this entry actually does exist, and it just sends the frame off through port interface 4.